Yeah, the topic is dynamic programming. This is one of the problem solving strategy. Just like divide and conquer and greedy method, dynamic programming is also one of the methodology for solving any problem. This is also useful for solving optimization problems, means the problems which require either minimum result or maximum result. So greedy method is also useful for same thing. Yes, greedy is also used for same thing, and dynamic programming is also useful for same thing. Now the name comes dynamic programming. A reason, there is a topic called linear programming in algebra, in mathematics. Linear programming. So there programming means a set of values, tabular values. So a table is called as programming, right? Set of values. So that is called as linear programming. So one by one we get all the values in a table, and those values will help us get some result. Now same table of values but not linearly, dynamically we will get the value. So that's why it is called as a dynamic programming. So dynamic programming means dynamically a table is generated, generating a table dynamically. This is one point. Then as this is for optimization problem, then you know well that for any problem there may be more than one solutions, right? K solutions. Second point about dynamic programming. Now suppose this is the optimal solution. This is the optimal solution, right? So it is feasible as well as it is optimal. When you can say that this is optimal solution? When you can say? In greedy method, we say that this solution is optimal because the procedure that we have used for getting the answer was optimal. The procedure was optimal. So in greedy method, do you find all solutions and then pick up the best solution? No, we follow our known procedure to get the best answer. Like for example, we have learned about minimum cost spanning tree. So for one graph, many trees are possible, many spanning trees. So few of them I have shown on board. So are we solving the problem by generating all possible spanning tree then selected the minimum one? No. Kruskal said that always select a minimum cost edge, you get the result. So in greedy method, we are following known procedure to get optimal answer. Whereas in dynamic programming, we will try all possible solutions for a problem, then we pick up the best one. So if a problem is having thousands of solutions, we will try to get all 1,000 solutions, it means. Yes, we will try to get it. Then that will be too much time consuming. That's why we follow some easy and simple method for indirectly generating all possible solutions. We'll not find each and every individual solution, right? Because for getting one solution or for getting some other solution, there must be some common thing. So we'll try to solve this common part. So this is common, suppose. So we'll try to get some common part so that we can get this solution also, and say whichever is best one. So again, suppose this is common for all three solutions. So that's how we will try to reduce the work for finding all possible solution. But definitely we will try all possible solution and pick up the best one. So that's the reason we are trying all possible solutions. So these problems are bigger in solutions. Their solutions are lengthier. So the algorithms used are lengthy algorithms. No doubt they are much faster. We are not directly trying each and every solution, but still the time taken for solving these type of problem is bigger, larger. Alright. So 2 points I told you. Why the name is dynamic programming? Second thing I said that in greedy method we don't find all solution. We directly get optimal. But in dynamic programming we will try all possible solution and say this is best out of all. So you'll find all possible solutions in dynamic programming, right? Two things about dynamic programming I told you. So one more thing I will tell you a little bit. See, in the GATE syllabus, dynamic programming is there in the syllabus, but they won't ask question because these problems are so big and so large, they cannot think of framing a question from this one. So it will take a lot of time for solving, and even a small problem takes a lot of time for solving. So they never ask any question, and in future also I guarantee you they never ask any question. Though in dynamic programming just the name they have given, and they will ask only one question from that. That is Bellman-Ford single source shortest path algorithm. They will ask only that one. So but the topic is interesting. Most of the students wants to know about this topic. So or they will not have clear idea about this one. That's why I'm covering this dynamic programming topic. Alright. So write down about two things. Dynamic programming is an approach for solving a problem by using a tabular method. Dynamic programming is a strategy for solving a problem using tabular method. That's why it is called as dynamic programming. Second point, it is used for solving optimization problem, that is either minimization or maximization problem. It is used for solving optimization problem, either minimization or maximization. Then next thing is dynamic programming approach will try to find all possible solutions for a problem, then pick up the optimal solution. Dynamic programming approach will try to find all possible solution of a problem and select the optimal solution. Principle of optimality. Dynamic programming follows principle of optimality. So you have to note down. I'll just dictate this one. See, a problem is solved in sequence of decisions. A problem is solved by taking sequence of decisions. A problem is solved by taking sequence of decisions. A problem is solved by taking sequence of decision. Whatever the initial state may be, note down, whatever the initial state or decision may be, whatever the initial state or decision may be, rest of the sequence of decision will be optimal. Rest of the sequence of decisions will be optimal if the first state was optimal. Whatever the initial state or decision may be, rest of the sequence of decisions will be optimal if the first state was optimal. If the first state was optimal. So indirectly, that's all, right? So indirectly it means the same thing, that try all possible solutions, then from that pick up the best solution, right? So when you are taking an approach, then that approach, every decision you should take a optimal one. So if the first one was optimal, then rest of them can also be optimal, not will also be. If the first one itself was not optimal, then rest of them, if you take them optimal part or not, will not affect at all. So it means actually, the meaning is that the actual meaning of the term, if I take, then every step should be optimal, starting from the first step. So right now you cannot understand this one. Once I take some examples, then you can get the clear idea. So let us take one problem and solve under principle of optimality. The problem is all pairs shortest path. What is the mean? First I will explain you. If there is a graph, like already we have used this graph, two, 3, 6, 5, 4, 1, 1, 4, 2. This graph already we have seen it, right? We have used this graph for single source shortest path, where this was the source vertex. We wanted to find the shortest path from 1 to 2. We found the shortest path from 1 to 2, 1 to 3, 1 to 4, 1 to 5, and so on. Likewise, we have also want to find 2 to 1, 2 to 2, 2 to 3, 2 to 4, 2 to 5, and 2 to 6. Likewise, we want a shortest path from 3 to 1, 3 to 2, 3 to 4, 3 to 5, and 3 to 6. Then we want shortest path from 4 to, then 5 to, and 6 to. So we want the shortest path between every pair of vertex. Every pair of vertex means between this also 1 to 2 as well as 2 to 1, 1 to 3 as well as 3 to 1, 1 to 5 as well as 5 to 1. Then 3 to 4 as well as 4 to 3. This is the meaning. So in a graph, maybe directed or non-directed, whatever graph is, in a graph we want to find the shortest path between every pair of vertex. So note down, if a weighted or non-weighted, if a directed or non-directed weighted graph is given, if a directed or non-directed weighted graph is given about the problem, right? Then the problem is to find shortest path between every pair of vertex. Then the problem is to find shortest path between every pair of vertex. Every pair of vertex. So example, path from 1 to 2 as well as 2 to 1. Path from 3 to 5 as well as 5 to 3, and so on. One solution for this problem. This is what we want. So solution is perform Dijkstra from 1, starting vertex 1. Perform Dijkstra from starting vertex 1. Then perform Dijkstra from starting vertex 2. Perform Dijkstra from starting vertex 3. So from 1 to all, then from 2 to all, from 3 to all, and so on. So if you find the shortest path to all vertices starting from 1, then starting from 2, then starting from 3. So Dijkstra, again you apply Dijkstra from starting vertex as 2. Again you apply Dijkstra on the whole graph as starting vertex as 5 or 6, like this. So you can repeat Dijkstra algorithm by changing the starting vertex. So Dijkstra algorithm can be applied repeatedly by changing starting vertex. Alright, it can be applied by changing starting vertex. For each vertex we can find Dijkstra shortest path. By selecting each vertex as starting vertex, we can perform Dijkstra. Problem is solved. Yes, problem is solved. Then Dijkstra takes how much time? Dijkstra takes order of n square time. We have already seen. Then for all n vertices, it will be n into n square. So this will be n cube. The time it will be taking us n cube. So for one vertex n square, right? For one vertex n square is the time. For n vertices, n into n square is the time. Alright? So this is one solution. So solution for all pair shortest path is One of the solution is apply Dijkstra on all the vertices, starting from source vertex 1, starting from 2, starting from 3. So write out this point in your own words. And the time will be n cube. If you perform the extra, time will be n cube. So this method, if you follow, then still you are following which method? Greedy method. Greedy method. Right? Is there any dynamic programming approach possible? Let us see dynamic programming approach for all pairs shortest path. I have explained you what is the meaning of all pairs shortest path. I am taking a graph. Suppose this is a directed weighted graph. Okay, this is a directed weighted graph. I have taken a small one because I already explained you that the solutions for these problems are very lengthy. So let us see how to solve this one. Let us see how to solve. That is a graph given. Then directed graph is there. So what are the vertices? 1, 2, 3. 1, 2, 3. 1 to 1 there is no edge. Then 1 to 2, 1 to 2 there is one edge with 4. Then 1 to 3 it is a 3. 1 to 4, okay. Then 2 to 1. 2 to 1 is 6. Then 2 to 2 there is no edge. That is infinity. It's a loop. 2 to 2 means it will be a loop. Then 2 to 3. 2 to 3 is 2. Then 2 to 4. Sorry, 3 to 1. Sorry, 4 is not there. 3 to 1. 3 to 1 is 11. 3 to 2 is infinity. Nothing is there. 3 to 2 there is no edge. Then 3 to 3 is also infinity. So this is a matrix, and this is a adjacency matrix. That is, for this weighted graph, this is adjacency matrix. So whatever the edges are there, I have taken them. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 edges, all edges are taken. 3 to 2 there is no path, so it is infinity. Self-looped are marked as either you mark them as 0 or infinity. We don't take care of them, right? We don't find path from 2 to 2. Alright, same vertex, we don't find the path. So let them be infinity only. Now, how to solve this one? Let us see. I am showing you dynamic programming approach. So let us solve this one. See, first take that matrix as it is. 1, 2, 3, 1, 2, 3. Values are infinity. I'll just put a hyphen here, right? Otherwise it looks congested. 2 and 11. This is infinity, right? We are not interested in, so dashes I have kept. This infinity we require. This is the first matrix. I will call it as A0. Same matrix, A0. Now listen, we want to know the shortest path between every pair of vertex. So first we will try to find out the shortest path between every pair of vertex going through vertex 1. Going through vertex 1. We'll generate a matrix to find the shortest path between every pair of vertex going via vertex 1. Going via vertex 1. So I will generate a matrix for this one. So now A1. This A1 means going through vertex 1. So let us see how to find out this one. So first of all, these are infinities, right? So these values not required. Then when we are saying via vertex 1, so in the matrix, first row, first column will be as it is only, because first row is vertex 1 only. So first row and first column will not change. See, I have taken a small example so that it is easy to solve. If I take some 5, 6 vertices, then many matrices are required and the problem becomes very lengthy. Okay? Problem becomes very lengthy. So that's the reason a small matrix is taken. Small matrix I have taken. Right? Now, let us solve this. We want to know whether there is a shortest path between the pair of vertices going via vertex 1. So between which vertices you will see? 2 to 3, 3 to 2. That's all. Via 1. So 2 to 3, 3 to 2, via 1. So let me find out A of 1 here, this value. That is 2 to 3. So 2 comma 3 I am writing. Okay. Yes. I have to take minimum of what? Present what is there here? A0 of 2 to 3. Or A0 of 2 to 3. Or 2 to 1, that is 2 to 1, then 1 to 3. 2 to 1, then 1 to 3. So 2 to 3 we are finding. So A0 of 2 to 1 plus A0 of 1 to 3. Let us take the values. Minimum of, what is the value here? 2, comma, what is the value here? 2, 1, 2, 1 is 6, plus, what is the value here? 1, 3, that is a 3. Out of these two, which is minimum? 2 is minimum. Write 2 here. Watch this carefully. See, what I have done is, in A1, I want to know whether there is a shorter path from 2 to 3. From 2 to 3, right? From 2, 3. Via vertex 1. So directly there is a path available 2, right? Or via 1, is it shorter? I have to check that. So I am taking minimum of current value, that as it is 2. Then 2 to 1, then 1 to 3. So 2 to 1, then 1 to 3. Add these two. So total is 9, but this is 2. So that path, existing path is better. Then next, A of 1, I have to find out this value. What is this? 3 to 2. So 3 to 2. So I should take minimum of A0 of 3 to 2, or means present value here, that is infinity, or 3 to 1 and 1 to 2. So in between 1 will come, 3 to 1 and 1 to 2. So A0 of 3 to 1 plus A0 of 1 to 2. So let us take the values. This is how much? Infinity. Right? So I have to put a bracket here. Infinity. Then A0 of 3 to 1. 3 to 1 how much? 11. Plus. Then 1 to 2. 1 to 2 how much? 1 to 2 is 4. 4. So which is the smaller? 15 is the smaller. So let it be 15. So we got this answer. So it means there is a shorter path between 3 and 2 via vertex 1, and that cost is 15. See, 3 to 1 is 11 plus 4, 15. Yes, it is there. Direct 3 to 2 is not there. 3 to 2 is not there. That's it. One matrix is sufficient to understand the whole procedure. Right? Take this one. Then I'll show you rest, because I have to erase this one. I have to remove this one. Then I will find out A2. 1, 2, 3, 1, 2, 3. Means the shortest path between every pair of vertex going through vertex 2. So going through vertex 2 means these are infinity. I'll take them as it is. Now second row, second column will not change because second vertex is involved here. So these are as it is. This is 15 now. So we should take the values from here. Now only which value 1 to 3 and 3 to 1 will modify. So I'll remove this. One, 2, 3. A2 of 1, 2, 3 is minimum of A2 of A1 of, that is from the previous matrix I have to take, A1 of 1 to 3 or A1 of 1 to 2 plus A1 of 2 to 3. So in between 1 and 3 you have to insert 2, 1 to 2, 2 to 3. So what is the value of 1 to 3? 1 to 3 is how much? 3, and comma, this is 1 to 2 is how much? 1 to 2 is 4, 4 plus 2 to 3 how much? 2 to 3 is 2, 2. So which is better? 3 is better. So take 3. Then I have to find out this value. A2 of 3 to 1. This is minimum of A1 of 3 to 1. Now in between these two I have to include 2. So A1 of 3 to 2 plus A1 of 2 to 1. So check it. A of 3, 1, how much? 3, 1 is 11. 11, comma. Then 3 to 2, how much? 3 to 2 is 15 plus 2 to 1 is how much? 2 to 1 is 6. So this is 21, this is 11. So 11 is smaller. 11 is smaller. So we got the second matrix. We got the second matrix. So in this way, now I will not show you the formula. Directly I will write on third matrix. So A3. So that's all. We have to prepare 3 matrices because there are 3 vertices. 1, 2, 3. 1, 2, 3. In this, these are infinity, right? And third row, third column will not change. So 11 and 15, and this is a 3 and 2. Then 4. This is 4, right? 1 comma 2, 1 comma 2, 4. So in between I have to take 3. 1 to 3, then 3 to 2. So this will be 18. So 4 is better. Then 2 to 1. 2 to 1 is 6. So 2 to 3 is 2. 2 to 3 is 2. Right? Then 3 to 1. 3 to 1 is 11. So this will be 13, but this is 6. So this is smaller. So that's it. We got the answer. So we got only one value updated in this one, that is 15. So this is the method you should perform. So the only focus was how to write, how to follow the procedure. Now, what was the formula we were following? For any AK of I comma j, we were finding minimum of, from the previous matrix k minus 1, we were finding I comma j, or else we were finding from the previous matrix A of I comma k plus from the previous matrix we were finding k comma j. That's it. Any one of these minimum we were taking. So k takes the values from 1 to n. So if there are 3 vertices, we should find out A1, A2 and 3, A3. So A1, A2, A3. So k will take the values from 1 to 3. This is the formula. Take the formula. So what is the time taken for this one? Time taken for this one is 1 matrix, 2 matrix, 3 matrix. So matrix takes how much time? Preparation of a matrix takes n square time because n square elements are there, 9 elements. Then how many times matrix is prepared? N times. So this is how much? Theta of n cube only. This is also theta of n cube. So the problem takes same amount of time. Even if you use Dextra, that is also taking same amount of time. But this is following dynamic programming approach. Alright, so it is trying out all possibilities and giving the result. So following dynamic programming approach. So it takes n cube. If you want to convert this into a program, then you have to take for I takes values from 1 to n, do. Then for j takes values from 1 to n, do. Then for k takes values from 1 to n, do. See, these two inner loops will be preparing a matrix and k is for preparing all the matrices from 1 to n. So 3 nested loops, so it is n cube. That's all. Next is 0-1 knapsack problem. Let us take the example. There are 3 objects and the capacity of the bag is 6 and the profits are given as 1, 2, 5 and the weights are given as 2, 3, 4. Now let us take this. We already know what is a knapsack problem, but this is little different. What is the difference? You have to take every object either completely or you have to reject it. So any answer, if I have to write answers here, then either I can write 0 or 1 or 0, anything. So I cannot write 0.5 here. I cannot write. So every xi value should be either 0 or 1. So fractions are not allowed. Means, I'll just repeat it. Knapsack problem means a bag is given and the objects are given. So for every object there is some profit and weight and you have to include the objects in the bag such that the profit is maximized. So you can include the objects in the bag. Fraction also you can include in knapsack problem. But here you cannot take the fraction. Means the objects are there which are not divisible. You cannot break them. You cannot break the objects. Right? So if you take it, you will take the full object or else you cannot take it at all. Alright. So this is x value can be either 0 or 1. So note on this one. This is same as knapsack problem of greedy method. Everything is there with you and greedy method I already have explained you. So it's same as knapsack problem of greedy method. But the difference is But the difference is we cannot take fraction of an object. Either we should take the complete object or completely leave it. Completely don't include the object. Either we should take the complete object or don't include at all. Don't include at all. So each xi can be either 0 or 1. Now we have to take dynamic programming approach. So in dynamic programming approach, already I told you that we will try all possibilities. All possibilities. See, the capacity of the bag is 6. So the total weights, if you add 4 plus 6 plus 3, that is 9. Right? It is coming up to 9. So we will try all possibilities and pick up the best solution. So we will try to put all the objects one by one, all combinations. So how to try that is we will follow a pair of, we will make a pair of profit by weight. We will make a profit by weight pair. Now directly I will show you the procedure how to solve this. Just watch this one. See, first of all we'll make a set with no profit and a no weight, nothing at all. Then I will prepare one set S01, so in which I will include first object. So when I include first object, profit is 1, weight is 2, so that you add it to this one. So 1 and 2. This is the order pair I got. Then I get a next order pair, that is S1, that will have 0, 0 and 1, 2. See, till here I stop and say, explain you. See, this order pair, this set is giving 2 order pairs. This means nothing is included in the back. This means first object is included in the back. That's what I told you, we will try all possibilities. We will try all possibilities. So till here we considered first object, right? So in this set we have considered or include first object, right? We have include first object. Then next we will prepare S11. In this set we will include second object, that is 2, 3. So we will add 2, 3 to both. So 2, 3 and 2, 3. So 2 is added to this one, profit is added, right? So this becomes 3 and 3 weight is added, so this becomes 5. So we got this order pair. So what we have done here, include second object. Now merge these two. So we get S2. So that S2 is 0, 0 and 1, 2, then 2, 3. I'm not writing commas in between. So you know they are separate. Now 4 possibilities are there. When you take 2 objects, 4 possibilities are there. No object is included in the back. Only first one, only second one, both are included in the back. Then I have to prepare S21. So here I will include third object, 5, 4. Add it to all, 5, 4, add it to all. So this becomes 5, 4. Then 5, 4 is added, so this becomes 6, 6. 6, 6. Then 5, 4 is added to this, so this becomes 7, 7. Then 5, 4 is added to this, so this becomes 8, 9. Then we will merge these two. So what we have done here, include third object. Include third object. We have included this one. So when I combine these, then I get set 3. So the result is 0, 0, 1, 2, 2, 3, then 3, 5, 3, 5, then 5, 4, 5, 4, then 6, 6, 6, 6. Shall I take 7, 7 and 8, 9? If you see the weight has become 7, weight has become 9. It's useless. I can simply discard these 2 tuples. I need not take them in solution because my weight is 6 only. So I have removed them there only. So I got the sets. No object included, only first one, only second one, and only third. Yeah, this is first and second, and this is third object, and this is combining what third and second first object. right? And rest of the combination, these are exceeding the capacity of the bag, so we have removed them. Now one more thing I will show you. Profit 1, weight 2. Profit is increased from 1 to 2. Then weight is also increased. Profit is increased 2 to 3. Weight is also increased. Profit is increased, but weight is decreased. So if you have two order pairs, PI and WI, and PJ and WJ, if you have two order pairs like this, where profit is increasing but the weight is decreasing or remaining same, so PJ profit is greater than PI profit, but weight of J is less than or equal to weight of I. How this is possible? You got the more profit, but the weight is reduced. So by including an object, the weight will increase, not the weight will decrease. So this is not possible. So what we do, we will discard this one. Discard PIWI, means first order pair. We discard this one. So what do you call to this? This is called as purging. This is called as purging. That's all. We have the solution. So the remaining order pairs are 1, 2, 3, 4, 5. 5 order pairs are remaining. Actually, we should get 8, right? 2 power 3, 8. But these are discarded, right? And one more is discarded. So 3 are gone. 2 are discarded because they are infeasible, going beyond the size of the bag. Now 1 is discarded because of purging rule, right? Because the profit is increasing, weight cannot decrease or weight cannot remain same. Weight should also increase. Okay, so you have to take down this one. Take an order pair of profit by weight. Take order pair of profit by weight and start making sets by including one object in each set. By including one object in each set. Follow this one. Then these are removed because weights are more than 6. This is removed because this condition is satisfied. In words you can write, between these two order pairs the profit is increasing but the weight is decreasing. If the weight is not changing or decreasing, then we have to discard this one. Discard this one. So we have discarded. Write on this, then I will show you solution. Now we have generated all order pairs. It is just like this. I'll show it here. See, first object not included, first object included in the bag. Then here, second object not included, second object included in the bag. Second object not included, second object included in the bag. Right? Then third object not included in the bag. Third object, I'll just write one here, included in the bag. Not included, included, not included, included, not included, included. See, if nothing is included, all are 0. Answer is 0. If only first one is included, means first not included, first one is included and nothing is included, then first one is included means 1, 2, 1, 2. If only second one is included, see, second one is included and nothing is included. This part if I take, second one is included, and nothing is included, then it is 2 comma 3. So we have 2 comma 3. So like this, how many solutions are possible? How many parts? 1, 2, 3, 4, 5, 6, 7, 8. Yes, we got 8, but these two are removed because they are infeasible, and this is removed because of purging. This is how we have tried. This is how we have tried. We tried all possibilities. So if you take the solution, see like this, we have tried what? This one is giving what? 0, 0, 0. Nothing is included. And this is giving what? 0, 0, 1. 0, 0, 1. Right? Then this one is giving what? 0, 1, 0. So 0, 1, 0. Then this one is giving what result? 0, 1, 1. So 0, 1, 1. Then this is giving the result 1, 0, 0. So 1, 0, 0. Then this is giving 1, 0, 1. This one is giving 1, 0, 1. Then this is giving result 1, 0, 0. So 1, 0, 0. And this is giving the result 1, 0, 1. Right? 1, 0, 1. And 1, 0, 1, how we got this one? Yeah. Oh, sorry. This is 1, 1, 1. 1, 1, 1. So 8 possibilities are there. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, right? 1, 0, 1, and 1. Yeah. This is 1, 1, 0, and 1, 1, 1. All 8 possibilities are there. So I have written all 8 possibilities. Now you can copy that if you want. Then I'll show you how to find a solution. Quickly, let us do it. One thing I will tell you. We found all possibilities for 3 objects, 2 power 3. So this is 2 power n. So the time taken by this procedure is 2 power n. It is exponential. It is exponential. Now we want to know which object is included, which is not included. Let us do it. See, highest profit by weight we will select. 6, 6. I am finding an answer, right? Which object is included, not included. 6, 6 belongs to S3, but it doesn't belong to S2. 6, 6 don't belong to S2. Therefore, third object is included. So if this order pair is here but not there previously, means we got it here only. So this object is included. Then result is 6, that is 5 we subtract and 4 we subtract. So the answer is 1, 2. Then we will check for 1, 2. 1, 2 belongs to S2. It is there in S2 here. And 1, 2 belongs to S1 also. It is here also. So second object is not included. Then we are still on 1, 2. 1, 2 belongs to S1 and 1, 2 doesn't belongs to S0. Therefore, X1 is 1. So the result is 1, 0, 1. That's all.